Once again, sorry about the delay. We'll see. If I need the pen, I may still have to go back and get that. But okay, I think this is the last thing we looked at last time, how you can sometimes sneak some categorical information into a scatter plot, which is normally not categorical. Okay, now, today, the formula for correlation. So, I guess write it down first, and then I'll try to get into parts and explain it here. Yeah, I'm sorry I can't make it simpler than this. However, let me just say this. You should find something familiar in parentheses. If you don't recognize it, I'll help remind you in a minute. So that's a small r on the left. Or r is reserved for correlation and statistics. And then there's one of our big old sum signs again. And that is an n minus 1 on the bottom there. So let me point out to you that that first set of parentheses, isn't that just the standardization almost? I mean, except for the fact that there's an x bar instead of a mu and an s sub x instead of a sigma. That's good old z equals x minus mu over sigma. That's our standardized formula. So, in effect, that first set of parentheses is just saying, for each point, what's the standardized x value? And for each point, that thing on the right is just the standardized y value. You notice the different notation? This is y minus y bar over the standard deviation of y. Okay, then take those two things, standardized x, standardized y, multiply them. Now do that for each point, add them all up, and divide by n minus 1. Kind of a long process, of course, that you won't really have to do manually. But it's important that you understand what's going on here. So it's saying, tell me how many standard deviations x is above or below the mean. Tell me how many standard deviations y is above its mean. Take those two standardized values, multiply them. Now do that for all the points. Add that all up. Divide by n minus 1. That's your correlation. And remember, if correlation is 1, well, it's perfect. If it's negative 1, it's perfect. If it's anywhere in between, it's imperfect, which is the way it normally is, right? You're not going to have, normally, you're not, for a lot of studies, you're just not going to get perfect correlation. Okay. So, I don't have my book with me, but what we wanted to do is take an example from the book. You guys could certainly look it up. It's evidently problem 4.8. It's on page 90. Maybe I could just borrow a book just to read the problem situation, and then I'll be okay after that. Thanks. Page 90. Classifying fossils. I'm going to try to pronounce that. Archaeopteryx is an extinct beast having feathers like a bird, but teeth and long bony tail like a reptile. Only 6 fossil specimens are known, but these specimens differ greatly in size. Some scientists think they belong to a different species. We will examine some data. If the species belong to the same species and differ in size because some are younger than others, there should be a positive linear relationship. So in other words, if we just have a problem of younger versus older creatures, you're going to find that the ratio of the, by the way, you remember how humerus, femur, so the top arm bone is the humerus, the length of that, and the femur is the top leg bone. And what they're saying, they're just kind of recording those two lengths. Okay, and if they belong to the same species, then the ratio between the two should stay approximately constant. Okay, that's the idea. So, here's the data that the scientists picked up. All right. Now, yeah, I'm going to just recreate this here. That was problem 4.8, right? Exercise 4.8, thank you. What I'm going to do is use the computer to, what can I say, to kind of redo in a long way. I'm going to make the computer do it in a long way, which is kind of silly because we can have the computer do it in a short way. But I want to do that so I can kind of show you the long way without having you go through the pain. Okay, so let me get to Jenzabar. And we log in. Statistics, Chapter 4. Okay. Exercise 4.8 is not there. Well, that's not good. Shoot. There's no table name for that or anything, is there? No. Okay, I'm sorry about this. I guess I'll just type it in. Okay, here we go. Okay, what do we have on the left? We had humerus. And on the right we had the femur, is that correct? Okay, could you read me the first point? Humerus. Femur. Thank you. The second one. What was that? 63? 63, 66? I still didn't quite hear that. Thank you, I'm sorry. It's another thing being... Okay.
70, 59, 72, 64, 84, or 74. What day the birds?
What does it say in the book? What's on the top?
Femur.
Okay. There. Now we got them in the right order. Sorry about that. Thank you for your help, everybody. Okay. Now, here's what we're going to do. I'm going to mimic that formula I just taught you. Okay? In order to do it, as you know, don't I need x bar? And I also need the standard deviation of x. And I also need y bar and the standard deviation of y. So in other words, I got to do the analyses things that we learned how to do in, I don't know, one of the early chapters. So, here, first of all, I'm going to do an automatic data analysis. So this is old stuff. I'm going to do descriptive statistics. And I want to do first this side, the femur lengths. And I'm going to put the answer, I don't know, somewhere over here. And I want the summary statistics. Surprising how long that's taking. All right, and then I want to do the same for the humerus. So, data analysis, descriptive. This time I want to do these guys. And this time we're going to put our results, well, let's start it over here. Okay. So now, mostly what I needed are two things for each. Here's my x bar. Here's my S sub x, standard deviation of x. Here's my y bar. and here's my standard deviation of y. Okay? I'm going to use those to start calculating this formula. Okay, so yeah, let's see. So here's going to be my x, which is in cell B2, and I'm going to subtract the mean, which is 58.2. I'm just copying that from the chart on the left. I should really have had parentheses around that. Sorry. And now I want to divide that by the standard deviation of x, which is 13.19848. Okay, so there's that first thing in parentheses. Now we can copy that in just a minute. Let's do the y now. So the y is what's in cell C2, parentheses. Yeah, parentheses. What's in cell C2 minus the mean of y, which is 66, close parentheses, divided by the standard deviation of y, which is 15.89025. Okay? Now, let's copy those down. Okay, those are all done. What's the next thing in the formula? After you figure out the two, I've got the parentheses done now. Now I'm supposed to take those and multiply each of them. Okay? So, here we have cell F2 multiplied by cell, what am I doing? Yeah, that's right, F2 times G2. Okay, cool, that's done. Notice we got a positive because we multiplied two negatives. Okay, there's all the products. Okay, now, next thing is the big Greek letter sigma. Add them all up. So this is sum of H2 to H6. Okay, we got the total. And now what's the last thing we do? Divide by n minus 1. So I'm going to take this last cell, which was what? H7. And we're going to divide by, how many did I have? 5? Okay, so there's the correlation. Now I'm going to show you how to do it in one fell swoop, but I wanted to demonstrate the formula. So I came up with a correlation of 0.994, and it goes on. That's really, really good. Remember, 1 is perfect. This is, wow. Usually don't get them that high, 0.994. Now, so all I was trying to do is demonstrate to you that there's all these steps. One more time. You take each x score, you subtract from it the x mean, and divide by the x standard deviation. Then with the y's, take each y value, subtract the y mean, and divide by the y standard deviation. Now take those two answers and multiply them. Okay, now do that for each point, and then add them all up, and divide by n minus 1. You got the correlation. R. Now, the quick way, which is much better. But I wanted to without doing the raw long way, the long way would have taken us about a half hour because we would have had to calculate the mean, we would have had to do all the standard deviation stuff. I mean, that's a major task. It would have taken us the whole period. So I kind of, in a weird way, simulated doing it the long way using shortcut. Okay, so now here's the shortcut. Data analysis, as you probably guessed. And now, for the first time, we're going to use correlation. There's actually a line for that. And then it's going to say, what's your input range? And now this is the first time we've ever clicked and dragged on 2 rows, but we need 2 rows. So, otherwise you can't get correlation if you don't have 2 variables. And then it says, all right, where do you want your output range? So same old deal. I'm gonna, I don't know, we'll put it down here. And let me explain. But first of all, do you see where column 2 and column 1 intersect? It gave us a correlation that agrees completely with the when I did the long way, 0.994149. Now, let me tell you what the rest of this is. You're going to think this is really silly, but what it's saying is, hey, column 1 and column 1, holy cow, they have a perfect correlation. That's saying column 1 correlates perfectly with itself. Duh. Okay. Well, here's what's cool about it. Well, yeah, and column 2 correlates perfectly with column 2. Of course, the only one we are really interested in here is column 1 with column 2. What's cool is if you have multiple columns, and let's say you have, a scientist often will have 8 or 9 variables, you can grab the whole 9 columns and do a correlation, and it'll tell you how every row correlates with every other row. Really powerful. I mean, it's like a month's work. Boom, just like that. And so this grid really, well, you may think is stupid, actually turns out to be really cool because it allows you to correlate. So like if I had 6 columns, it would have columns 1 through 6 going this way, columns 1 through 6 this way, and wherever they intersect, it tells you how 2 columns are related. And then you can just look for high correlations and go, whoa, column 3 and column 6 are really closely correlated. So even though I didn't do a multi-column, this output really does make sense. Yeah, I don't know if I may have to come up with an example of a multi-column tomorrow. Does anybody remember any in the book where they had like more than 2 variables? I don't think there were too many in there, but I'll get one and I'll put it in there and I'll show you what I mean. So it's great. Okay, now if you don't want to mess with all of that, you can also give, and I've neglected to do this much, you can also give a command. So you can go, if you like putting in formulas, you can just come in, give it an equal sign so it knows you're doing a formula, and then you can type. I love this. As you're typing, it nails it. It gets down. I put CO for, I know correlation starts off that way. You notice it's now got it nailed down to the CO commands. R. Oh, and there it is. Correl. Correlation. Now I got to give it the array, the first array, which means I got to go from cell what? B2 to B6. Love it. Look at it. Highlighted it on the right. Now I'll give array 2, variable 2, C2 to C6. Okay. Close parentheses. And so you can do it with a single line command too. As you can tell, I'm leaning towards having you use the data analysis commands because they're nicely built in. It's a little easier to use dialog boxes. But Excel does prompt you very nicely and helps you out. And then it does a very good job of saying, well, here's what I still need yet. So anyway, you notice again I got the same number. So this thing has a really good correlation. So what would happen if I plotted the scatter plot for this? I mean, just already, the fact that the correlation is 0.99 something, what does that tell you about the graph? It's going to be increasing, going uphill, and because it's close to 1, yeah, awfully straight. Remember when it got to be 0.6, then it got a little fat, but it still kind of was heading in the same direction. Well, this is really lined up. So let's do it. Let's prove it. Let's quickly do a scatter plot. Remember how to do that? In 2007, you simply go highlight your data, do an insert, pick a scatter, and disconnected.
And you can see they really are quite lined up, aren't they? Not a surprise. They're not perfect, but boy, they're awfully lined up. And that's what the .994 was telling you. So, there's your first taste of a correlation problem. I wanted to demonstrate. So, what do I need you to know? You need to know this formula. And you need to know a little bit about it. So if I throw that on there, and then I said, what does that mean? You got to be able to say, oh yeah, well, there's the standardized x for each coordinate on the left, multiplied by the standardized y for each point, and then take all those products, add them up, and divide by n minus 1. That you understand that's what's going on is important. And then the other thing you need to know is what does a correlation score mean? You need to know that perfect is either 1 or -1, and anything in between is varying degrees. A 0, of course, is no correlation, points just scattered everywhere, but when the numbers get closer to 1 or -1, it's looking really lined up. What's the difference between a negative correlation and a positive one? I'll get a good example of positive correlation. Student effort, student grade are often positively correlated. That means as one goes up, the other goes up. But an example of, in science, of negative correlation is as if you have an enclosed space, as pressure goes up, the temperature also goes up, but as pressure goes up, the volume goes down. As pressure goes down, the volume goes up. Those are negative correlations. Well, what's another one? As temperature goes up, snow shoveling goes down. I mean, that's a real corny one, but a good example of inverse. Okay. All right, you get the idea. I think we can head back to this guy. So anyway, that was the idea behind this. This slide shows you the individual, at least a little, what we just did, so that when you refer back, you'll see a kind of a trail of what we did. Yeah, here's the plot. Now there's a line connecting there. I might as well just show you how to do that, even though it's next chapter stuff. So let me go back to the spreadsheet. This is really cool stuff that's coming in chapter 5. You can just take any one of your scatter plot points, hover over it. First thing that's really cool is the computer gives you the ordered pair. See that? This one here is 64, 72. If you right click on any point, you can say add trend line. And then there's a choice. We're going to want linear. And then, really cool, you can display the equation on the chart and display R squared. And just like that, it prints the best fit line, puts it right on there, the one that cuts right through the center of everything, and it gives you the equation. And it gives you R squared. Now, let me explain. R, we just calculate, right? Was 0.994 something? If you square that, you'll get this number. A lot of times that's displayed, and I don't want to spill the beans too much. We're going to learn what R squared is going to be important as well as R. We're going to get to it later. So anyway, here's a little view of the future. Right now, you're not required to know how to do this. Chapter 5, we're going to be doing it. So we're going to be doing more with scatter plots in chapter 5. So Excel has some absolutely wonderful tools that are built in. Let's just quick do the bird. Remember the bird problem with how many birds return to the nest? Percentage of birds that return to nest versus new birds that join. Not the nest, but what did they call those? Groups. What was the word they used? Wasn't flock. Oh well. Nobody else remembers it either. There was some word that they used there. Colony. That's it. Thank you. And what number problem was that in the book? Thanks. So I'm going to just quick. Four, wasn't it? Yeah. I want to just quick call that up. Thanks. Let's just do a correlation on this. Okay, manual. Automatic. I'm not going to do another manual with you. But, so one more time. We want to do data analysis, pick correlation, highlight both columns, output range. Well, let's bring it back over here, and that should do it. And you can see there we got a negative 0.7448. Negative 0.748 is not bad, and it's going downhill. Let's just do it the raw way. Equals Corel, array 1, A2 to A14, array 2, B2 to B14. Close parentheses. Yep. See how we got the same number? Okay. Correlation. And this is what a negative 0.748 looks like in correlation. As you can tell, they're grouped. They're definitely heading downhill, but they're certainly not perfect. There's some spread. That's why it's not negative 0.9 or something like that. Okay. Okay. Example 4.4. Understanding state SAT scores. Let's see. Okay, you have your books handy. I don't. But it says figure 4.1 shows a clear form. There are two, you guys got that picture? Figure 4.1. You see how there's kind of two clusters of points on there? So we got almost like two separate things going on there. Okay. It says in the cluster at the right, 52% or more of the high school graduates take the SAT, and the average scores are low. The states in the cluster at the left have higher SAT scores, and no more than 36% of the graduates take the test. There are no clear outliers. That is, no points fall clearly outside the clusters. What explains the clusters? So sometimes you can actually tell, well, what's going on here? There's two separate groups. There are two widely used college entrance exams. The SAT, which is more Michigan, the East and the South, and the ACT, which is just kind of unique to the Midwest. And that's hard to explain, but Midwest would include states like Ohio, Illinois. There's a bunch of states. It's not just a couple up here. Each state favors one or the other. So, for example, Wisconsin is ACT. If you're in Michigan, I can tell you right now it's SAT. It's just kind of the State Department of Education, I guess, makes a declaration and says, I want everybody to use and then they tell you. This select group of students so anyway, in ACT states, most students who take the SAT are applying to a selective college. So in other words, if you're in Wisconsin the only reason you would probably take an SAT is you want to apply to a college that's in an SAT region. Like maybe you wanted to get into MIT or something, okay? And so maybe MIT says, oh no, for us you got to take the SAT. So even though you're in Wisconsin, you can request to take the SAT because you want to get into a certain college. Okay. This select group of students has a high, so guess what? People who want to do that, who want to go to a school that's pretty selective and out of their region, are probably going to be better students, aren't they? I mean, students who go really far away, generally speaking, are already looking at like some specialty that school has, or they're looking for a better scholarship. They tend to be better students. Not always. Students that, and so it's hard to make generalizations, but that's what the book is saying. So in the highlighted area, the relationship in Figure 4.1 also has a clear direction. States in which a higher percent of students take the SAT tend to have lower average scores. This is a negative association or negative correlation. Association, correlation are synonyms, and you'll see those used interchangeably. So, in the box, positive association, things are heading in this direction. Positive slope from algebra class. Negative association, things that head in this direction. It doesn't matter what angle they're on, just so they're going downhill. Just like in algebra when you had a negative slope. Some people have said to me about how do you remember if you read it from left to right or right to left. I said just remember in America, the same way you read text in America, from left to right. If you just keep that in your head, oh yeah, left to right downhill, negative. Okay, and finally, the strength of the relationship is in a scatter plot is determined by how close the points are to a form, the line. Here's some points about correlation. This is in your book on page 91. This is worth looking at. And I've highlighted, I'm sorry, this is awfully small up here. I've highlighted just parts of things that I think are big. Number one, correlation makes no distinction between explanatory and response. So when you, for example, get a correlation of 0.994 like we did today, did that tell us which variable was the cause and which was the result? It's just an unbiased measure saying, wow, those things really go together. When one goes up, the other goes up. When one goes down, the other goes down. They act together. Number two, correlation requires that both variables have to be numbers. They have to be quantitative, obviously. Three, because R, that's correlation, uses standard values of the observation. Remember how we used X bar and Y bar a few minutes ago? And how we used S sub X and Y sub X? And then we calculated the standardized X and the standardized Y. Because R uses standardized values of the observations, R does not change when we change the unit of measurements of either one or both. So in other words, if you were doing like, I don't know, lengths of bones like we did earlier, the length of a bunch of humeruses and a bunch of femurs, and at first our scientific data was in centimeters, we'd get a correlation, and we could change all of them into inches, and we'd get exactly the same result. Why? Because we're standardizing them. This is kind of cool. So standardization, that X minus X bar over S sub X, that's basically making it unit neutral. And it makes it's an unbiased measurement. It has nothing to do with what units of measure you use at all. You could call the ones on the left inches and leave the ones on the right you could do in furlongs. As long as you measured it accurately, the correlation would not change. That's pretty cool. So that's unique. And so it's another nice thing that standardization gives you. Yeah, so the last part of paragraph 3 says the correlation R itself has no unit of measurement. It's simply a number, 0.994. It's not 0.994 inches, it's just 0.994. Number 4, positive R indicates a positive association, negative, a negative association. Number 5, correlation is always a number between -1 and 1. Values near 0 indicate either very weak or no relationship. Okay, let's go down to number 6. Correlation measures the strength of only a linear relationship. So, what if we had a pattern that looked like this? Let's say we plotted our scatter plot and it looked like this, like a parabola. Correlation does us absolutely zero good in that case. Okay? So correlation is only for finding straight line relationships. Are there other things that can be used to do that? Yes. But we're going to be zeroing in on, we want to know if it's a straight line linear relationship. Okay? So just so you know, correlation doesn't work for curves. And number 7, like the mean and the standard deviation, the correlation is not resistant. R is strongly affected by outliers. So here's a little bit of bad news. R, like the mean, is what? Is kind of fickle and is greatly affected by outliers. So that's bad news, and it might mean that before you do a correlation, with careful consideration, you might want to think about taking an outlier out of the group first. Or investigate, why is that an outlier? Maybe, you never know. Somebody was ticked off and they were giving you opinions and they thought they'd take it out on the person doing the questionnaire and you get this obnoxious outlier. Or maybe the data measurement, guy was drinking too much Kool-Aid before he took his measurements and maybe the Kool-Aid was spiked, I don't know. But anyway, there's something inaccurate possibly. Okay. In general, even though I did it the other day in class, R is not so easy to guess just by appearance. Remember, I did some eyeballing and I said, yeah, this is pretty good. It's about a 0.6. Yeah, generally speaking, it's pretty hard to do that. I like that. This is going to be part of your assignment, but please note this. To explore how extreme observations can influence R, use the correlation and regression applet. Now, let me remind you, on the website, you see how whenever there's an applet mentioned, you see how I have a link to it here? So under Chapter 4, you see there's a correlation and regression applet. My guess is you probably are supposed to do that for one of the assigned questions too. So I put a link there to make it a little easier to find it. And those applets are pretty easy to use. I would encourage you to follow through on it. Okay, back to here. Looks like this is this is a problem of the icicles, where they did a run. Yeah, they did 2 runs of icicles. I don't remember what page that's on, but it must be in Chapter 4. Also, look at the high correlation on this one. Here it is up here. 0.9956, even better than the one we had earlier. And then just a couple of slides to kind of finish this up. Death from superstition? Is there a relationship between superstitious beliefs and bad things happening? Apparently there is. Chinese and Japanese people think the number 4 is unlucky, because when pronounced, it sounds like the word for death. Sociologists looked at 15 years of death certificates for Chinese and Japanese Americans and for white Americans. Deaths from heart disease were notably higher on the 4th day of the month among Chinese and Japanese, but not among the whites. The sociologist thinks that the explanation is increased stress on unlucky days. So obviously the number 4 is not causing danger or death. But what do you think? You think if people are extra nervous about it, they might have a little more likelihood of having a problem? Yeah, nervousness, it's a good example of what happens if you're really stressed. It's harder on your body. And so if you're always under stress, guess what? Your body's going to be a little bit weaker. If you're always like really tense, how many times have you ever driven on practically glare ice? I remember driving from Minneapolis to Milwaukee, and I was driving somebody else's car, a professor's, and so I was scared to death. I'd have rather wreck my own car. I didn't want to wreck somebody. It sounds dumb. I didn't want to wreck mine either, but I remember I had such a grip on that steering wheel. I think I almost melted part of it. I was, I just like, and I had to go approximately, I don't know, I wasn't able to get up to 15 miles per hour because I'd lose control. It was that bad. And so, was I tense? Oh my. I got out of the car, somebody had to pry my hands off the wheel, and my hands actually hurt. And my whole, you know what that's like. So anyway, there's an assignment in here somewhere. Yeah. First, look at this quote. I love this. Niels Bohr, by the way, won a Nobel Prize. He said, "Prediction's difficult, especially of the future." That's supposed to be humorous. Okay? I mean, isn't that the only kind of prediction? And, see, you haven't seen this yet, but we're going to take these lines, and we're going to say, well, let's use that line to make a prediction. What will happen when we get, where will we be on? First, when you do that, be careful. Prediction is got all kinds of problems. Here's the assignment. You probably knew that already. I think it's on the website. Now, when does it due? In 2 classes, so on Monday. Yeah. Sorry about being late today.